Hello, Mr. Sorrentino here, and I'm doing another video for Math 31, and this one deals with section 5.2, exponential functions and their graphs. Um, in the first section, we talked about functions and their inverses, and that's because of the fact that the rest of this particular chapter, we're going to talk about these exponential functions and their inverses, which are known as logarithmic functions, and how we do various mathematical things with those. But let's talk about what an exponential function is and focus some attention on it and talk about some of the concepts you need to know from it. An exponential function, I mean, powers are involved, but notice the main difference is that, we were used to situations, with polynomials, we had x raised to the n power, and we had maybe multiple terms of that. Notice now that we now have the number as the base and the x as the exponent. That's what makes them exponential. We're always going to assume that a is greater than 0, because if we have a base that's negative, that creates a different situation altogether, because of the fact that, if I have a negative base, then raising it to an even number power, even integer power, would make it positive. An odd power would make it negative. There are some powers that wouldn't work at all, like fractional powers. So we would run into some issues with continuity and things of that nature. So we don't really consider those, and that's important to keep in mind. So these bases, they are only going to be positive numbers. What's important about that is if I have an exponential function and a has to be greater than 0, and a is not equal to 1, so we're assuming that a is not going to be 1 raised to some power, because 1 raised to some power is just 1. That means that if f of x equals a to the x power, we know that its range, from a very standpoint of a basic function like this, is going to go from 0, not including 0, to infinity. It's going to be a positive number. I cannot raise a positive power to an exponent and get a negative result, or even get a 0 result. Now, when a is more than 1 and when a is between 0 and 1, it's going to create other issues. We're going to explore those momentarily. But let's talk about the exponential function f of x equals 3 to the x power. And again, we're going to kind of demonstrate this by kind of focusing our attention on this. I mean, this would be a parent function, because I'd have different parent functions depending on what a is. So 3 to the x power would itself be a parent function. And of course, all parent functions, we tend to center around x being 0 when we try to discover what goes on there. This requires us to know some exponential rules from previous algebra courses and whatnot. Like, for instance, 3 to the 0 power, or anything to the 0 power, is 1. 3 to the first power is 3. 3 squared would be 9. 3 cubed would be 27. If I have 3 to the negative 1 power, remember, negative powers means reciprocal. So now we are talking about negative 1 being a reciprocal, because we actually are doing it as a power of a constant. So that's going to be a 1/3. Whereas if I do 3 to the negative 2 power, I can think of that as 3 to the negative 1 power squared, because remember, raising a power to a power means you multiply the exponents, and that means I'm doing 1/3 squared, which would be 1/9. And very similarly, if I raise 3 to the negative 3rd power, I get 1/27. So if I plot these points, now the 0, 1, 1, 3, 2, 9, and 327 are pretty easy to graph with the way this is scaled. The 1/3 and the other ones are getting pretty close to the, being nothing. But my graph for this function looks generally like this. Notice this has a horizontal asymptote on the left only. Because, as we mentioned before, since this is a positive base, I raise it to an exponent, it's going to be positive. But I'm going to get, as I keep making this number more and more negative, this is going to get closer and closer to 0. Since we are, in general, moving up, we can move from left to right, this is considered to be an exponential growth function. Now, there's going to be others as we study them. But that's what an exponential growth function looks like. For example, 2 deals with a very similar function. You're going to see a lot of the same numbers in it, because we're doing 1/3 to the x power. Well, 1/3 is just the reciprocal of 3. So you're going to see some of these numbers just in different spots. Like, for instance, if I do 1/3 to the 0 power, I'll use a different color for this one, that's 1. If I do 1/3 to the first, well, that's 1/3. 1/3 squared, that's 1/3 times 1/3, that's 1/9. 1/3 cubed is 1/3 times 1/3 times 1/3, that's 1/27. These are what we saw for the negative x's on the previous graph. And that's because, likewise, if I do 1/3 to the -1 power, that means the reciprocal of 1/3, which is 3. If I do 1/3 to the -2, well, that's like having 1/3 to the -1 squared, and 1/3 to the -1 was 3 squared. 3 squared is 9. And very similar, this would be 27. So the exact same numbers, just in different spots here. So, these functions, are very closely related to each other. As a matter of fact, if I did a reflection, a horizontal reflection, or basically a reflection across the y-axis of y equals 3 to the x power, it would be this function here. And I'm going to show that. I have -327 would be a point, -2,9 would be a point, -1,3 would be a point, 0,1 still a point, 1 1/3, and of course the graph would look an awful lot like this. And again, now this one has a horizontal asymptote on the right, because again, as I keep getting a bigger and bigger value for the what I raised 1/3 to, let's finish the word here. This is going to get smaller and smaller. But this is what we would call an exponential decay. Notice that 3 is a value that's more than 1, and 1/3 is a value between 0 and 1. So that's a rule we're going to come up with as we go into this. And as a matter of fact, it's highlighted in the very next item. Given an exponential function, f of x equals a to the x power. If a is greater than 1, then the function is an exponential growth function. If a is between 0 and 1, then it's an exponential decay function. Eventually, we're going to have situations where we need to set up some problems, and if we're being described as having a decay problem, and you end up setting up a function that's a growth function, it's not going to work, and we're not going to find any answers to this. Each graph has a horizontal asymptote at y equals 0, since a of x is greater than 0. Just remember, though, the horizontal asymptote for a growth function is left only, the left side of the graph only, and for a decay function, it's the right side of the graph only. It's not like a rational function where I have a horizontal asymptote where the end behaviors are working on both sides of the graph. They're only on one side only. So, but you could be asked to do many other different things with these functions. You could have exponential functions that look a lot like this. These are just, for me to figure out what this is, it's just the same kind of thing we did all the way back in chapter 1, using our graph transformations. So for instance, if I wanted to figure out what's going on with g of x here, I'm going to note that the parent function is y equals 3 to the x power, and then I have this table. And so knowing your powers or being able to come up with a list of powers of certain numbers becomes handy, because again, this was 1, 3, 9, 27. These were just the reciprocals. Now I have to look and see. Now I have to remember that my parentheses are technically around the x. I don't really need to have it for that version of it, but it's around it. So anything in the exponent, any operation going on in the exponent is, going to be a horizontal transformation. Anything being multiplied or added to the base is going to be vertical. So when I look at this first one and I say, okay, use graph transformation techniques to draw the graph of this. This is all inside the parenthesis, the 1/2 is on the outside. So when I start defining what my x and y transformations have to be, well, the y, I see multiplied by 1/2 is outside the parentheses. The 3, remember, is the base. It's part of the function. I'm not going to do anything with the 3 because the 3 was already handled by making my table. So my y's are all going to be multiplied by 1/2 because I do exactly what I'm told to do for vertical transformations. So all of these y's are going to get multiplied by 1/2. So 27 divided by 2 is 13.5. 9 divided by 2 is 4.5. 3 divided by 2 is 1.5. 0.5. 1/6, 1/18, 1/54. Now the x's are a little bit more complicated because one, I have to remember that I always perform the exact opposite operation. I have to note the difference between sign of the numbers and the operation. And I also have to make sure that if there's more than one transformation going on, I have to apply the order of operations in reverse. When I see negative x minus 2, I see a multiplication of -1 and subtraction of 2. Which means that based on what we talked about before with these, that means I need to first, I see a subtraction of 2, it means I'm going to add 2, and then divide -1. It's the opposite operation. So I'm not going to say, because I have some students who will say, oh, I multiplied by -1, so the opposite is multiplying by +1. No. Multiplying by -1, the opposite operation is dividing by -1. They just happen to do the same thing. So each one of these x values I'm going to add 2 and then divide by -1. So -3 plus 2 is -1. Divide by -1 is a +1. -2 plus 2 is 0. Divide by -1 is 0. -1 plus 2 is 1. We have -1. And all these are going to just kind of go, you kind of get the idea of what they're going to be along the way. So now I have what I can do to plot this now. Now I could go back and say what these are. I mean, the multiplying the y's by 1/2 is going to cause a vertical shrink by a factor of 2. The divide by -1 is going to cause me to multiply all my x's by -1s eventually, or divide by -1, which is going to basically cause a reflection across the y-axis. I'm also seeing an addition of 2, which means I expect to see, I'm going to add 2 to my x-coordinates, which means I'm going to shift 2 to the right. So those are all the operations that are going on. And let me emphasize the axes on this, because they sometimes just have a nasty habit of disappearing when I make these graphs and convert this over. So when I plot these points now, some of them are easier than others, like -5, 13.5. I could probably guess is about here. -4, 4.5. About here. Negative 3, 1.5. That one's pretty straightforward. That'd be right here. Or negative 3, 1.5. There we go. Had that in the wrong spot. Negative 2, 1/2 would be about here. These other values get really, really, really small, so I was going to look at this being mostly a graph that does this. Now notice, one of the things I wanted you to key on here, I had a positive A value, but this is a decay. But the reason why it's a decay is because the x coordinate was multiplied by a -1 at some point up there, which causes me to divide -1. When that kind of thing happens, and I have that reflection across the y-axis, it may look like it's set up as a growth, but as soon as I see that I have a negative exponent or a negative x on that thing, it's like me having the 1/3 raised to a power instead of a 3 raised to a power. So it's going to behave like a decay. So keep in mind that when we obey those rules, it says, a to the x, we're assuming that x does not have a negative exponent on it at that time. If it does, then those rules kind of get reversed about whether it's a growth or decay. Let's look at B. I'm still starting with the same function. So the parent is still y equals 3 to the x. And the table is going to be the same. Now I'm going to look at the transformations I have, again recognizing that the exponent is where the quantity, where the parenthesis technically is. The 3 is part of the function itself. I'm not going to be doing anything with 3 here because I'm not seeing any kind of operation with 3. 3 is the base of the exponential. And so what I see here on my x's, I see an addition of 1, so I'm going to subtract 1 from all my x's. Remember, I always do the opposite for these horizontal transformations. So when I start setting up my table, all of these just simply go down by 1. The y's, I see a multiplication of -1, I see a subtraction of 4. I do both those operations, I follow the order of operations. So I'm going to multiply -1 and then subtract 4. So 27, I'm going with the numbers that are easier to compute, the integers. 27 times -1 is -27. Subtract 4 is a -31. 9 times -1 is -9. Subtract 4 is a -13. 3 times -1 is a -3. Subtract 4 is a -7. 1 times -1 is -1. Subtract 4 is a -5. -1 times a third is a -3rd, which gives, when I subtract, I'm going to get -4.3 repeating. -1 times 1/9 is -1/9. Subtract 4, I'm going to get -4.1 repeating. And -1 times 1/27 is a -1/27. And that's going to give me like a -4.037 repeating. I mean, it's also important to notice. I mean, remember we have asymptotes on these things, and so I mean I can note here that this had a horizontal asymptote left only of y equals 0. Well, the fact of the matter is, since I have these transformations, if I take this, multiply by -1 and then subtract 4, this would have a y equals 4 as the horizontal asymptote. And I still would expect, and since there was really no kind of like reflection, that affected horizontals, I expect to have the horizontal asymptote still be on the left only for this one. So let me re-emphasize the axes a little bit better on this. And I'm going to plot these points. 2, -31. Let's say roughly is about here. 1, -13. We'll say is roughly about here. 0, -7. We'll say is about here. -1, -5 is about here. -4, as far as an asymptote goes, would probably be right about here. Should help me figure out how to get this graph going correctly, because I would expect that it's kind of following this and it starts branching down as well. Since we're getting negatives with this wouldn't really define a situation of exponential growth or decay. It's just, it's a lot of transformations on this. But that's generally how you go through and do these particular transformations. The next thing we talk about with dealing with exponentials is the compound interest. So let's talk about what the formula looks like, and then from that formula, what kind of things go on with it. So compound interest, you're going to see this, like they're going to talk about this in this section. Kind of shy away from it for a little while to talk more about logarithmic functions and solving logarithmic equations and things of that nature. And then we'll get back into talking about exponential growth and compound interest, which is a type of exponential growth. We'll also talk about exponential decay as well. But as far as exponential things go, we have this formula to follow as far as figuring out compound interest. So we have A, which is the amount after time t. Sometimes you'll see this referred to as the accumulated amount. If we put an amount into a bank account and we let it collect its interest, it's going to gain some, it's going to get more money because of the interest, and it's going to accumulate. That's what, hence the accumulated amount. P is the initial amount, which will sometimes be known as the principal. That means what you're putting in there and depositing originally. For the circumstances that you are going to be given in this course, you are not going to be assuming that, we're not going to handle situations where we're putting money into the bank and taking money out of the bank. There's more sophisticated formulas you have to handle with that, and some of them you don't even have formulas. You have to kind of just go on with what's known and compute them accordingly. The situations you're going to be given is if we're going to put money into this account and we're not going to touch it. We're not going to add any more ourselves. We're just going to let the interest accumulate. R is the interest rate in decimal form. So if I say we have 5% interest, R is 0.05. If I have 7.9% interest, a big issue that students will do is they'll say, oh, 7.9 interest, already a decimal, so 7.9 is R. Well, no, this is still written as a percentage. I need to write it as a pure decimal. That means that R is 0.079. If I say R is 7.9, that's like saying 790% interest. It's often mistakes with the R value where students will, come up with an obscene amount of money just by doing a simple compounding. It's like, I invested $1,000 and for 20 years at 4.9% interest, and that's going to give you more money. It's not going to give you an exceptional amount of money. I'll have students that'll say, "Oh, I invested $1,000 at 4.9% interest, and 20 years later, I have $60 billion." That doesn't happen. You know, that doesn't make any sense. That'd be, I mean, if that were the case, everybody would be billionaires. They'd be able to sock away a little. I could put $1,000 away, work, and and for 20 years, and then come back to $60 billion. I'd be, they wouldn't have these retirement funds and things like that. I mean, that you have to invest and constantly put money into. So, it doesn't make any sense for that. So that's often because they put the wrong decimal in for a percentage. With compound interest, T is typically the time in years, and N is the number of times the interest is compounded in 1 year. This is sometimes it's also known as the compounding period. We're going to explore how we handle these in example 4 below. So let's have a look. And excuse the size I have this set at for example 4. It's just that the setup is very similar for all of these, except, anything that's going to be different. I mean, we're assuming that we have an initial investment or principal of $5,000. We have a 6.9% annual percentage rate, so that's our interest rate. Will be worth 10 years, so our T is 10, and they mentioned different compounding periods. So essentially, for all of these, I'm going to have A equaling 5,000 times the quantity, one plus R, which is going to be 0.069. I'm going to hold off on N for a second, but the T is going to be 10. So all these are going to be identical in this fashion. All it's going to be different is the compounding period. So when you see compounded annually, that means that I'm just doing this once per year. So N is going to be 1. Semi-annually means N is going to be 2, twice a year. So 2 would be here, 2 would be there. When I compound interest, once I determine the period of interest, and say it would tell me that we don't usually have anything that by wording this that will tell us 3 times per year, but sometimes you might see a problem that says we're going to compound the interest 3 times per year. That means we take the interest rate, split it into 3 equal parts, and apply it at 3 equal intervals of time. So, when I see quarterly and N equals 4, I'm going to take the interest rate, divide it by 4, and apply it 4 times in that 1 year. But I'm going to do that 10 times because there's 10 years. Monthly, it's going to be N is 12. Compounded daily, if you want to be overcritical and say 365.25 because of leap year stuff, but we'll just say 365. And compounded hourly, well, you have to figure out, 24 hours a day for 365 days. That's 8,760. You're not going to see many problems asking you to compound hourly. We want to talk about, we want to show, though, the effect of compounding alone, because in all these instances, we have the same starting amount. We're going to invest it for the same amount of time. We have the same interest rate. How does compounding the interest make a difference? So let's run these calculations at this time. So I come up with money amounts. Now when I make these calculations, and I'm going to do these calculations quickly and put them in, keep in mind I'm going to be rounding off to 2 decimal places because that's the way we round off money. Another pet peeve thing, make sure dollar signs go before the number because that's the way we express them. Don't put them after the number. I won't mark you wrong, but you'll probably get a quippy comment from me if I see it in the wrong place. So let's have a look at these, see what they look like. That I came up with when I calculated these out, following my order of operations and everything. So if I invest $5,000 at 6.9% annual percentage rate, and if I'm only compounding the interest once a year, I'm going to end up with $9,744.22 after 10 years, assuming I'm not putting any more money in there. Which, it's a pretty good jump. I mean, I'm going up by 47 $4,744.22. When I compound it semi-annually, so instead of taking the interest and just putting 6.9% at one time during that year, if I take that 6.9%, split it into 3.45%, and apply it twice during the year, that means I'm going to take 3.45% added to the of 5,000, added to the 5,000, get a new amount, and then take 3.45% of that amount, and then add that to the total. I end up with $9,853.26. So you can see, I'm talking about a difference of about a little over $109 there. So I mean, that's a pretty significant difference. If I go quarterly, I ended up with $9,910.10. Now it's even higher, but if you look at the difference, this splits it into four pieces and applies it four times a year. It's not as big of a jump as when I went from 1 to 2. I mean, here I'm going from 9853 to 99110. So I'm going up maybe about roughly maybe $57. A little less than that actually. So I mean, the first one was like a good 100 and some dollars there, 109. This was more like, it's about 57. When I go to the next one, from four times a year to 12 times a year, it's still higher, but the difference between the two is only about $38. And then when I go from 12 times a year to 365 times a year, well, that's, it's still higher yet, but the difference from, doing it monthly is only about, roughly about $19. And when I go to hourly and basically, every hour, I've split the percentage into 8,760 equal parts and apply it 8,760 times during the year, I end up with still yet a higher amount, but now, we're less than $1 difference. I mean, so compounding alone will increase the amount of money you get, but there's a limit to it. It only goes so high. It's only going to take it so far. And we're eventually going to talk about an instance where we compound interest what's called continuously. That means that we essentially take a year, break it down into an infinite number of infinitely small parts, and we take the interest rate and break it into an infinite number of infinitely small percentage points and apply it an infinite number of times. That would be the maximum I could possibly get just from compounding at that interest rate. We'll talk more about that when we get into some other concepts with it, but it will eventually come. But, there's obviously a limit to this. And this kind of gets into an idea of a special exponential base that we tend to start looking at when we deal with exponential functions. So let's have a look at that. And before you think about it, this is not a typo. It says the number e. It's just like the number pi. This is going to be an irrational number that we're going to define from this. So I'm taking my compound interest formula here, and we're going to assume that we have p equals 1, r equals 1, and t equals 1. So essentially, what we're looking at here is that our formula is now going to be a equals 1 times 1 plus 1 over n to the 1 times n power. And we want to see, okay, well, if I just change n, what happens with this? And here are the values that I get when I do this and put these numbers in. So I'm going to put each one of these values into that function I just came up with and get a result. And these are just doing some roundings of this number. But as you see, when I just change the compounding of this number, the end value, I get this, it starts at 2 and it keeps increasing until I get to this. And as I go from next higher power, the next higher value of n, and so forth, this starts having a limit where, I start going to a number that's about 2.7182817, so forth and so on. And so what ends up happening is if you keep going and making n bigger and bigger and bigger, the more decimal places stop changing, and you end up with a number as we approach infinity, as n keeps getting infinitely big, that's about 2.7182818,284, and it keeps going on, but there's no discernible pattern to it. It doesn't show signs of being a rational number. There's no repeating pattern in the decimals. There's no sign of termination. This number is what we define as E. So this is what we're calling E. It's an exponential base where essentially, and the whole premise behind E is that, growth, a lot of things grow percentage-wise, um, you know, just growth in general for plant life, even human beings. We grow, in an exponential fashion, but it's continuous growth, and that's the idea behind the E. It's assuming that we have continuous growth. Continuous growth, is basically like, like if even if someone has what they call, quote, a person as a growth spurt, it isn't as though, if they grew like 6 inches in a year, it isn't like, during the course of the year they were 5'6", and then the next thing, sitting in front of you, they show up 6 inches right in front of you and become 5'6". No, that doesn't happen. That 6 inches growth occurred continuously throughout the year. Well, this E is kind of behind the idea of doing this continuously. When I do the other growth and do compound interest, I'm splitting it into discernible amounts where I am going to have, a sudden jump of value. And the more times I change that compounding period, the bigger that number is, the more continuous the growth is being applied, and that's the way things in biological systems tend to use. So a lot of biological systems will use this exponential base, although a lot of things that they explain can be used with other bases. This is also the exponential base used in calculus a lot, and there's reasons behind that. I'm not going to get into for this course. That isn't going into other concepts that we're not going to need to know about. So now that we have this exponential base, we're going to look at the function f of x equals e to the x and some transformations of that. Now, as we do this graph here, there's going to be a limit to how precise we can be, especially with a value that's irrational. And having all these decimal places, I'm not going to be able to graph it with too many decimal places of accuracy. So for the sake of our exercise here, I'm going to work under the assumption that E is approximately equal to 2.717, which is good enough. Or the 718, take that back, 718. And even now, I'm not going to be able to graph all that accurately, but just for the sake of computations and whatnot. And so essentially, if I, raise that to the first power, I'm going to have 2.718. I raise that to the 0. Anything to the 0 is just 1. The rest of these, I'm going to have to apply powers. So if I square it, I get 7.3, we'll say 87. If I cube it, I get about 20.079. Again, I can't be overly accurate with these as far as the graphing goes. I want to get an idea where these are. but I'm not going to be able to do too much with it because of the fact that, I mean, these are going by ones, my X and Y coordinates. I can't, you know, if I'm going to put like 1.3 and 1.36, the the differences between the two are minuscule to none when I'm graphing it on a graph like this. So I want to be as accurate as I can and kind of get a good idea where these things go. But I'm not going to be able to do it like, perfectly as it is, so I don't have to have too many decimal places. I just want to have an idea of where it should be. We'll say about 0498. What about 0.05? And so I can plot all these points to the best of my ability. 0, 1, I mean, one nice thing is that, raising the 0 power is always going to give you a 1. But if I have an irrational number and I raise it to a power, I'm going to have more irrational. So this is about 2.7 something or other here, which I'll say is about there. At the square, it's going to be at it's going to be at 7.387. So we'll say a little under 7.5. At 3, it's going to be at about exactly. It's pretty much at just slightly above 20. As far as the rest of them go, they're going to get closer and closer to the x-axis. I'm not going to be able to get too precise with that. So I'm just going to kind of just graph it at this point. Still looks like a growth function. It's just a different base, that's all. But if I use a table like this, I can come up with an approximate now if I do some other powers of e. And again, the reason why we did these graph transformation techniques is so that I know I'm not missing the important parts of this. Because again, if I have a graph that looks more like this one, gotta get my drag thing going. E to the negative x plus 2. If I just start putting random x values in and seeing what's going on there, I mean, I might just focus on this part right here on the graph, and I might think, oh, it's on the graph it almost looks linear, and I think it's linear. And I've had students make those kind of conclusions before. And that's why having an idea about graph transformation techniques becomes useful, because I'm less likely to make those mistakes if I realize, well, okay, if I have a parent function and I set it at 0, and I do this as a transformation from beyond that, I can see where the important things are happening, where the asymptote may be, and things of that nature. So, and as I see, I'm going to note here that this had a horizontal asymptote at y equals 0. Because that's also a vertical feature for this. So if I have a vertical transformation, I expect that to be transformed in a vertical way too. And so when I look at e to the negative x plus 2, and I want to get an idea what's going on with this, well, the x coordinates from what I see there, I mean, again, the negative is inside the parenthesis. That's being multiplied to the x, so I have negative 1 being multiplied, which means I'm going to divide my x's by negative 1, which is the same thing as multiplying them by negative 1. It's just going to change their signs. And the y's, since the plus 2 is on the outside, it's a vertical transformation, I'm going to add 2. Which also means that the horizontal asymptote is going to be added by 2 as well. So y equals 2 would be the horizontal asymptote, which is an important thing to know, because I want to know where it's starting to behave like the asymptote, so I can start assuming that's where it is. I certainly don't want the graph to go below there, so if I misplot anything, it may cause an issue. So basically all these are going to be added by 2, so this is going to be 2.0498, this is going to be 2.135, this is going to be 2.368, this is going to be 3, 4.718, 9.387, 22.079. So if I start plotting those points, 0, 3 would be about here. Negative 1, 4.71 would be close to that 5. Negative 2 would be at 9.38, so roughly about there. 3 at 22.07, so we're talking about there. And I could graph this. You know, the rest of them are going to get closer and closer to the horizontal asymptote. So knowing where that's supposed to be, I can start graphing and say, okay, I'm going to get closer, 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 and start getting infinitely close. And there's a good graph of what that looks like. And if you graph this on the same kind of axis, it'll look exactly like that. So again, we're trying to draw these accurately with as few points as drawn as possible. So, and that brings me to the end of this video, dealing with exponential functions. In the next one, we're going to talk about its inverse logarithmic functions. But in the meantime, if you have any questions on exponential functions, please make sure to bring them up in class or come and see me during my office hours. Until I see you at one of those locations and situations, or until the next video, I'll see you around. So have a good day.